So last time we talked about how average velocity can be thought of as a slope of the secant line. And this is another way to think about it. When you hear about velocity, you hear miles per hour usually. But the number on the top is a distance number. So the miles per means divide, and the hour is the time units. So when you hear about the average velocity, you hear about the distance, change in position, over time, change in time. And so if you look at a graph, let's say s of t, a lot of times they'll let s be the position function. Well, here the black line, t squared, is the position at time t. So at time 0, it's at position 0. At time 1, it's at position s of 1. And s of 1 you get by plugging 1 in for t there, and you get 1. So the y value at s of 1 is 1. And at time 2, 2 seconds later, the t value is 2 squared, which in this case is 4. So if I wanted to find the average velocity between t equals 1 and t equals 4, well, it would be the change in position over the change in time. In this case, at 2, it was at position 4. At 1, it's at position 1. So I get 3. The average velocity is 3 feet per second, meter per minute, miles per hour, whatever the units are. But that 3 turns out to be the slope of the red secant line that connects those 2 points. The change in position was the y value, and the change in time was the t value. And so that's why we can think of the average velocity as the slope of the secant line between those 2 points. Well, ideally, that secant line wouldn't touch the graph in 2 points, which is the average velocity. If we could get it to touch the graph at a single point, we'd have the instantaneous velocity, which is the velocity you would feel at that exact moment. So the same graph, s of t is t squared, and this time we're going to look at t equals 1, and we're going to look at the slope of the tangent line. All the tangent line means is it only touches the graph in 1 point instead of 2. And this is the tangent line at t equals 1, because that's the place it touches. So again, we came across the problem of just touching a line at 1 point. How are we going to do that? We need 2 points to make a line. And so we fudge a little bit. We step over distance h. And we get another point 1 plus h. So we have plug in 1 plus h. And we have plug in 1. When we plug in 1, we get 1 out. We saw this before. So the y value at 1 plus h means you plug in 1 plus h for t. And you have to FOIL that. And you get 1 squared, which is 1, plus 2h, plus h squared. So that's my second position. My first position was s of 1, and this is where I got my 1 from. It's just 1 squared. So the blue line would be the secant line between 1 and 1 plus h. And if I get that h to get smaller and smaller, that blue line gets closer and closer to the red tangent line. Well, if I'm trying to find the slope of the secant line, I get the second position, which is at 1 plus h, minus the first position, over 1 plus h was my second time, minus 1 was my first time. And I get s of 1 plus h minus s of 1 over h, because the 2 1s add to 0. Plus and minus. Well, s of 1 plus h is 1 plus 2h plus h squared minus s of 1 is 1. And again, these plus and minus 1s add to 0 here. And I get the slope of the secant line is 2h plus h squared over h. Now, in a perfect world, that h would be 0. If that h was 0, then that red line would be the only point where it would touch, because 1 plus 0 is just 1. So the 2 points would be the same t value, t equals 1. But right now I can't plug in 0 for h. But it always works out that if you do this right, you didn't make any errors. You can cancel the h by factoring. And you're left with an expression that you can plug 0 for h into. So to find the tangent line, which would be the slope, or to find the slope of the tangent line, which would be the slope of the red line in the graph, because h would be 0 then, and so 1 would be the second point as well. Well, this is the limit, as h goes to 0, of the slope of the secant line. And the slope of the secant line, when we started off, was s of 1 plus h minus s of 1 over h. And I couldn't put in 0 for h because there's an h on the bottom. But after I said so, let me just write it out again, in case you've forgotten what it looks like. 1 plus 2h plus h squared minus 1 over h. Can't plug in 0 for h. But if I simplify it, I can do that. The limit as h goes to 0, remember the 1's canceled, and I factored out an h. And it's the same as the limit of 2 plus h. But after I simplify it, now I can plug in 0 for h. I couldn't do that before because the h was on the bottom, so I had to simplify it. And I get 2. The slope of the tangent line is 2. This is called the instantaneous velocity. Also known as the slope of the tangent line. So this is at t equals 1. Let me rewrite that. And that's also known as the slope of the tangent line of the position at t equals 1. Instantaneous velocity is the slope of the tangent line, whereas average velocity is the slope of the secant line. And so what we're going to talk about next is this idea of a limit. And the limit is putting in a number that originally you can't plug in. Like in our previous example, when we had our original equation of the secant line, we couldn't plug in 0 for h. But after some simplification, we could plug in 0 for h. And so that lets us actually look at a point where there's only one point, yet we can still calculate the slope. The tangent line only touches this graph at a single point. But we were able to calculate the slope of that tangent line by first moving an arbitrarily small amount over, and then letting that small amount get closer and closer to 0. So, some ways to look at a limit. When we have a limit is really a two-sided feature. A limit is a y value. Or a dependent variable, dependent value. As you approach an x value, which is the independent variable. Because sometimes they use s and t, like you did in the example above. The one you solve for is the dependent one. And we have left side limits. We have right side limits. Or left hand, right hand, sometimes they're called. And two-sided limits. So we look at the left-hand side limit and the right-hand side limit, which always exist, and we use them to determine if the two-sided limit exists. If the left and right side limit are equal, the two-sided limit exists. If the left and right-hand side limits are not equal, the two-sided limit does not exist. So the way to remember this is this only exists the two-sided limit if the left side limit is equal to the right side limit. Otherwise, it does not exist. So that's a good way to think about it. We look at the two one-sided limits, left and right, and if they're equal, the two-sided limit is that. If they're not equal, they don't. So if I want to find the limit, so we'll go to the next page. If I want to find the limit of some function, we'll call it f of x, as x approaches some number a. The left-sided limit is notated as the limit as x approaches a with a little superscript negative sign of f of x. And the right-sided limit that's signified with the limit as f of x as x approaches a from the right-hand side, and that's a superscript positive. And that's the notation that we use to denote the limit from the left or the limit from the right. The two-sided limit if this exists, the left and right-hand limit have to be the same. So we didn't need the plus and minus on the a, because it's the same from both sides. So the symbol that denotes the two-sided limit is the limit as x approaches a, because we don't need the plus and minus of f of x. So the first one is said the limit as x approaches a from the left. The middle one is the limit as f of x approaches a from the limit of f of x as x approaches a from the right. The limit of f of x as x approaches a from the left, and the limit of f of x as x approaches a. The left side, the right-sided, the left-sided, and the two-sided. And we can find these graphically. If I have a graph, y values and limits aren't necessarily the same thing. -1. We'll let this graph be the picture of f of x. And I can ask you to find out some things about f of x. For example, I could ask you, what is f of 1? Well, the 1 there is replacing the x in the parentheses. So what f of 1 means is what's the y value when x equals 1? And when I go to x equals 1 and I look at the y values, I see there's two circles. There's one that's filled in and there's one that's not filled in. The one that's filled in is the y value. So the one that's filled in this case is at y equals 2. So the y value at f of 1 is 2. But I could also ask you to look at the limits. I could ask you to look at the limit as x approaches 1 from the left. So let's look at the left-hand limit as x approaches 1. Now that's the way we would denote that. The x approaching 1, the negative means from the left of f of x. Remember, a limit is a y value. So it's asking you, what y value are you getting close to as x is getting closer to 1 from the left? To do that from a graph, pretend that you're walking on the graph just as close as x equals 1 as you can get, except from the left. If I'm walking on the graph here, when I look ahead, it looks as if when I get to 1, the y value is going to be 1. So from the left, that limit looks like I'm going to approach y equals 1. So the limit from the left is 1. I can also look at the right-sided limit. I can look at the limit as x approaches 1 from the right. Now that's a 1 with a plus sign as we denote it. And to find that limit on a graph, I imagine I'm walking on the graph just a little bit of the right of 1. So I got to walk on the graph to the right of 1. That'll put me right there, the red figure. And if I were to look ahead and say what y value does it appear I'll end up at if I keep walking to x equals 1, that y value looks like y equals 2. So the blue person on the left thinks it'll be 1, the red person on the right thinks it'll be 2. It's different from the left, it's 1, from the right, it's 2. Since it's different from the two sides, then that plus or minus on the 1 is very important. And if I take it off to write the two-sided limit, I get dne. But that dne stands for does not exist. It doesn't exist because it wasn't the same from the two sides. And that's the only way we can get a limit to exist, is if it's the same from the two sides. Well, let's try that again. Let's try that at t equals 2. Ooh, let me do something here. Change the graph a little bit. I'll ask you some more questions. For example, E. I could ask you, what is f of 2? Well, 2 is in the parentheses where the x is in the function. So that means replace the x with 2. When I replace the x with 2, if I want to find the y value, I got to look for where it's shaded in. Here at 3, there's an open circle, so that's not the y value. The y value is up here at 4. That's where it's shaded in at x equals 2. And where it's shaded in are the points we're keeping. So the y value is actually 4. Now if I look for the limit, I can look for the limit as I approach 2 from the left, and the limit as I approach 2 from the right. Oops. Let's write this in a different color. How about blue? The limit as x approaches 2 from the left of f of x. And that's what the little negative sign means, from the left. So I need to stand a little bit to the left of 2 on the graph and walk towards the number 2. As I walk towards the number 2, it looks like the y value is going to happen at 3. So even though the y value is really up here at 4, and there's a hole there, if I look ahead, it looks like the graph will go to y equals 3. That jump up to 4 is a surprise. Now if I look at the right-sided limit, now that's g. This is denoted the limit as x approaches 2 to the right of f of x. And that's what that superscript plus sign means. And if I were to stand a little bit to the right of x equals 2 and walk towards x equals 2, again, the y value is going to look like it's going to happen at 3, even though the real y value is up here at 4. The limit, if I were walking on the graph, it looks like that would occur at 3. So in this case, if I take the plus or minus away, I can actually find the limit as x approaches 2. Since it's the same from the right and from the left, the limit as x approaches 2 is 3. Now let's do some more. What if I ask you to find f of negative 1? Well, what that means is find the y value when x is negative 1. And if I go over to negative 1, I see a hole. That hole is at y equals negative 1. But it's a hole. It's an open gap. There's nothing shaded here. Nothing at all. If there's nothing shaded here, that y value doesn't exist. And a lot of times people will write the empty set. Or does not exist also works. There is no y value. So I can find the limit from the left and the right. If we look for the limit from the left, the limit as x approaches negative 1 from the left of f of x. That's what the little negative on the superscript means. Well, that means I need to stand to the left of negative 1 and look and see where the y value appears. It appears the y value is going to be at negative 1 as well. So as I approach negative 1 from the left, the y value looks like it'll be negative 1. Now I'm going to look at what happens if I approach negative 1 from the right. So I put a superscript plus sign of f of x. Well, if I stand to the right of f of x, a little bit to the right, on f of x of negative 1, and I look where I'll end up, it looks like the y value will be negative 1 there as well. Since it's the same from both sides, then I didn't need the plus or minus on there. That two-sided limit, as x approaches negative 1 of f of x, must exist as well. And that'll be negative 1, because it's the same from both sides. So you'll notice in 2.2 they have some graphs where they ask you to graphically find limits from the left and from the right. And then you use these limits to determine whether the two-sided limit exists. You can also find points as well. So let me do an example where we find a graph of a function that has certain limits, and then we'll check some limits by tables. And in the next video we'll talk about computing them algebraically. So here's number 25. And it wants us to draw a graph. So sketch a graph having the following characteristics. So 25, g of 1 is 0, g of 2 is 1. G of 3 is negative 2. The limit of g of x is 0 as x approaches 2. The limit of g of x as x approaches 3 from the left is negative 1. And the limit as I approach 3 from the right is negative 2. Now there's more than one graph that'll work, but I want to draw one that does. And so the first thing I'm going to do is put my points on the graph. That's x equals 1, x equals 2, and x equals 3. And I know the y values of these points. At 1, the y value is 0. At 2, the y value is 1. And at 3, the y value is negative 2. So I put in my 3 y values. A, B, and C. Now I have some limits. This first one is the limit as x approaches 2, and there's no plus or minus superscript. So that means as the graph approaches 2 from the left and the right, it goes towards y equals 0. So the actual y value at 2 is 1, so I can't have a closed circle there at y equals 0. I have to put an open circle at y equals 0, because the actual y value is 1, and that's where I need to shade it. But I know the graph gets close to that 0 as I come in towards it. So if I were walking on the graph, it would look like it was at the x-axis, y equals 0, even though the real y value is at 1. And then it doesn't say anything about the limit as x approaches 1 from the right and left. So I can assume that it's a nice smooth graph. So I just have to draw a graph. The only other place I have limits to worry about is at x equals 3. And it says from the left it looks like negative 1, and from the right it looks like negative 2. So I need, negative 2 is already filled in. At 3 the real y value is negative 2. And from the right hand side that limit's got to look like negative 2. So my graph is going to look like it's supposed to end up there anyway. The limit as x approaches 3 from the right is negative 2, and the y value at 3 is negative 2. So here if I stand on the right, the limit looks like negative 2 from the right. But from the left, that limit should look like it's negative 1. So I need an open circle at negative 1. And if I walk on my graph towards 3 from the left, I would need it to look as if the graph stopped at negative 1, even though the real y value is at negative 2. So here's an example of a function g of x that would satisfy the given conditions. So at 1 the y value is 0, at 2 the y value is 1, at 3 the y value is negative 2. The limit from both sides as x approaches 2. From the left it looks like 0, from the right it looks like 0. So the two-sided limit should be 0. But when I walk on the graph towards 3 from the left, it looks like I'll end up at negative 1. When I walk on the graph from 3 towards the right, it looks like I'll end up at negative 2. So that's an example of how you can draw a graph to fit certain limit qualities. The other topic I wanted to talk about really quickly was how you can find limits from a table. So this is problem 11 in the book. It's in 2.2. And it has us calculate the limit as x approaches 2 of x squared minus 4 over x minus 2. Now, one way to calculate a limit is just to plug in. And sometimes when you plug in, the limit exists. It'll just pop right out. But in this case, when I plug in 2, I get 0 on top and a 0 on the bottom. So I can't plug in to find this limit, because the limit's 0 on the bottom. Or because I get 0 on the bottom when I plug in. But we're going to learn some techniques to make this limit doable. Well, one way to look at the limit is to find the left-sided and the right-sided limit. So if I look at the limit of x squared minus 4 over x minus 2 as I approach 2 from the left, well, that means I need to plug in numbers smaller than 2 if I'm approaching it from the left. X and f of x. So in number 11, this is 1.9, 1.99, 1.999, and a 1 with 4 nines. This will give us the limit, or an idea of the limit, as I approach 2 from the left. So what I'm going to do is plug these into my calculator and see what I get. So when you plug 1.9 into your calculator to calculate what this will give you, you have 1.9 squared minus 4 divided by 1.9 minus 2, which is 0.1. And that gives you negative 3.9. Well, now I take 1.99 and plug it in for x. 1.99 squared minus 4 divided by 1.99 minus 2.